The third aquifer test method we're going to go through is the slug test method. This is for a single well in an unconfined aquifer, so it's very convenient to know the hydraulic conductivity right around a monitoring well or something. We did lots of these for underground storage tank sites. So it's for unconfined aquifers, so it calculates the hydraulic conductivity. It does not calculate the storativity. So the way it works is you lower the water level in a well quickly. There's also a method you could raise it quickly, but typically you lower it quickly. Well, like a 2-inch monitoring well is not that much water, so if you have a pump, you can zoom, you can pump it out really quick, and then you monitor it as the water comes back in, and then you plot the drawdown. So it's going to start out high because it's going to start with a big drawdown and come back. You plot that on a log scale drawdown versus time on a linear scale. Initially, there's going to be some water right around the borehole, so the borehole is bigger than the well casing. So you have, and then you put the gravel around there. So the first water that's going to come back in is coming from that gravel pack around there. But after that, then it's coming in from the aquifer, and how fast it comes in represents the hydraulic conductivity of the aquifer. Kind of like we did with the Cooper-Jacob method, we find the slope of the line by choosing 2 points along there. It's another graphic method. People did some really clever stuff before everybody had computers. So I'll show you in a second. We pick numbers off there that are used to get the slope. And then we have this equation. This is, there's been a couple variations on it. This, again, is from the Octasolve software. It has slightly different terminology in there than we do on our page. I actually copied from the Bouwer-Rice method itself. You can do this in Octasolve. It was developed by Herman Bauer and Bob Rice. They develop an equation that the hydraulic conductivity is RC, where RC is the radius of the casing, that's the pipe, times the log of R, big RE over RW. RE is the radius of influence, over RW is the radius of the hole, the borehole, over 2LE. LE is the screened interval of the well. So if you have a 5-foot screen, it's 5 feet. If a 10-foot screen, it's 10 feet. And then 1 over T, we'll pick T off there, the log of 2 points, Y0 over Y at some later time. RE is the radius of influence. Bad news, there's no way to know RE. For an exam, I might actually give you an RE, wink, wink, to make it a little easier to calculate. But what we actually do is we estimate this term, this log of big RE, the radius of influence of RW, from a graph. And we have different equations for different situations. So a partially penetrating, your well LW does not go all the way down to the ground. We're going to do an example where it's fully penetrating, so actually our LW goes all the way down there. So partially penetrating is LW is less than H. H is from the water table down to the bedrock there. Fully penetrating is LW equals LH. So you can look those up in various places. I'm going to show you. So this is what it looks like. We have initial drawdown here. This is in meters, actually. The first reading, you can set up your meter to read off in a bunch real quickly and then less as time goes on. But we had 3.64 meters of drawdown. So what's that, 10.5 feet, 11 feet, something like that. And then it comes back, so the drawdown gets lower. So initially the water comes in quickly. This is from the borehole right around the well. It comes in quickly, and then eventually it comes into kind of, you see a straight line here, and then after a bit, just the way the equation works, it deviates from that. But that straight line portion is what we want to look at. And then to get that slope, we pick off a couple points. We pick off the y of t, my line isn't very straight here, so I'm going to say my t is 36 seconds, 36 seconds, and then my y at 36 seconds, I'm going to say is 0.1, and that's in meters. I can take any point along there. I could have actually taken, so look at the 20 second one or 18 seconds. So I could have taken one of these points here as my y of t and my t of 18 seconds, or I can take anywhere along this straight line. So then the other point I need is the y0. The y0, and I've given lots of quizzes and tests on this. Y0 is not the first point there. The Y0 is the extension of that straight line up there. So it's the intercept of the line. And this one, it looks to be about, this is 1 meter to less than 3. I have, in my calculations, I have 2.2 meters. Again, my line isn't very straight there. You could take a straight edge and do better than that. This equation is based on 1 over t log of y0 or y over yt. That's really the slope of that, just like the Cooper-Jacob method. So the y0 here was 2.2 meters. Again, this is not actually the drawdown at time 0. It's the drawdown at time 0 if we extend this straight line up there and hit the axis there. Our selected y value at time t was our y was going to be 0.1 meter at 36 seconds. And I'll put that right down here at 36 seconds. And I'll also write that right there. All right, now the tricky part. We want to get this. We can't get the radius of influence unless I give it to you in a test. We want to get that combined term. The way we get that is we get, for the fully penetrating version of it, it's that combined term is 1.1 over the log of LW over RW plus C over LE over RW. So we have those values. LW is 2 meters from the water down to the bottom. H is 2 meters. Borehole radius is 0.06 meters. Remember, that's the radius. So it's, a 6-inch hole would have a 3-inch radius. The casing and screen radius is 0.04. Saturated screen one is also, in this case, 2 meters, equal to the other. It's screened over the whole interval there. All right, so we have this funky equation here, and we need to pick C off the graph for this. A and B is for other, when it's partially penetrating. All right, so we have our, here on the bottom, LE over RW on the x-axis, and that is, I've calculated that out here, it's 33.3, and then at 33.3, I'm going to zoom in here. So this is 10, 20, 30, 40, 50, so 35. So going straight up from 30, I'm hitting about there, 33. So this is 2, 3, this is 2.5. It's a little above 2, I'm going to say, because this is what I use in my calculation. I'm going to say C equals 2.5. It's probably a little lower than that, but let's go with that. So I'm going to zoom back out here. We'll put a 2.5 in there. Again, it's probably a little lower than that. All right. So the log of RE over RW equals, brackets, 1.1 over the log of LW over RW. I'm going to write it out here. Plus C over LE over RW. And that whole thing to the minus 1. So if I plug in here the LW over RW was 33.3. LE over RW was also 33.3. C was 2.5. So if I plugged it in and again take the inverse of that, I have written down that this equals the log of RE over RW equals 2.57. So we'll plug that into our equation. I'm going to go here and repeat a couple things that we just did. So we had our line through here. We hit a T of 36 seconds. And again, I could have taken it off there where we got a Y of 0.1. We extended this up here and we hit a intercept of 2.2 meters at T equals 0. So our Y is 0 was 2.2, and then we had a 0.1 at a T of 36 seconds. So now we'll plug it into our equation. So K equals RC is the radius of the casing. So that's going to be the 0.04 meters. So again, a 6-inch well would be a 3-inch radius. A 4-inch pipe would be a 2-inch radius. So what did I just say? There's 0.04 meters squared times the log of RE over RW, which we determined that whole term together is 2.57. I'll say it for a third time. In a test, you might be given the RE, and then you'll have to plug in the RW and take the log of that. And that's over 2 times LE. Oops. 2 times LE, where LE is the screened interval. Those are all the L's are going to be 2 meters here, but that's it's 2 meters in this case, times 1 over T. Our T was 36 seconds, times the log of Y0, which was 2.2 meters, over our selected time, YT is 0.1 meters. And I think if you plug that all out, you get K equals 8.8 times 10 to the minus 5 meters per second. Is that high or low? 10 to the minus, that'd be 10 to the minus 3 centimeters per second. The only number I have in my head for landfills, a liner has to be less than 10 to the minus 7 centimeters per second. So this is pretty high. And that comes out to 7.6 meters per day. So again, hydraulic conductivities can vary widely. We did a lot of these tests from our one site. It was, we did our slug tests and the water didn't come up and didn't come up. And then it got to lunchtime and we went and had lunch and came back and didn't come up and didn't come up. And I mean, it's coming up barely. Left it overnight, came back the next day. So it was it was basically clay. It was super low, but it's a good way to get a hydraulic conductivity, and it gives you hydraulic conductivity right around the well you have here. Hydraulic conductivity is very heterogeneous. It varies a lot in space, but this is a good method to get it around that well. So the slug test was the third of our methods here for aquifer test analysis as a specific type of aquifer test.